So we've done now the data instructions in ARM, and we're going to move on to the load and store instruction in ARM. This is how we're going to get information from memory into the machine and back again. These are quite complicated in ARM. There's a lot of really interesting options. And so we're going to spend a little bit of time here. The instruction for load and store looks like this. The 27 and 26 are 0 and 1. And don't forget, those are the two bits that really specify what you're doing. 0, 0 means a data instruction. 0, 1 means a load or store instruction. But after that, R, P, U, B, W, L, S are all different flags that specify exactly what kind of a load store instruction you're doing. And then you have RD and RN. RD specifies the destination, which is the register for the load and the store. And RN specifies the beginning of the address, whether the address is offset by some other value, we'll see in a minute. And the rest of it is all specified in these 12 bits at the end. So in some ways, it's similar to a data instruction where you've got two registers specified and then 12 bits of like a bunch of other stuff. But the difference is you've got all these flags, and each of these flags specify what load store instruction you're talking about. Some of these flags are fairly simple to understand, and some of them are a little more complicated. So we'll start with the simple flags first. LS just means are you loading or you're storing. So if it's 1, you're loading. If it's 0, you're storing, right? Load means move from memory into a register, right? From RN into RD. Store means move from a register into memory, right? The specification is the same. It's store word, STR instead of LDR, store register, load register. But the order is the same. RD is still the place in the register file you're poking at. Whether you're moving from or to, it depends on whether you're storing or loading, but the specification is the same. So LS is load or store. Whoops. W, we'll skip for a second. B is byte or word, right? Are you loading or storing 8 bits, or are you loading and storing 32 bits? Very simple. The rest of it is a little bit complicated. R is whether you are adding well, let's get into it in some detail, first of all. There are a lot of different options, and the options all depend on what you're doing in memory, right? Oftentimes, when you're loading and storing in memory, you're actually interacting with a data structure of some kind. You've got an array, for example, and you're going to increment your access to that array one to the next. Or maybe you've got a linked list where you're incrementing your array based on some new address or pointer to the next chunk of the linked list, or whatever. ARM builds in all these options to look at the different ways of accessing memory. And so usually what you do is you have a pointer, right, an address, and then from that address you have some offset that says maybe you're pointing at the beginning of the array, and then you got some offset from that beginning of that array, whether that's a register offset or an immediate offset. And the second thing that you do is update where you're pointing to next. And you might do that before or after you do the access, right? Depending on how you construct your code, you might say, the first thing I'm going to do is update the pointer. And now I'm pointing at this element in memory. And then I'm going to access it, right? That's pre-indexing. You're changing the index first and then accessing it. Or you might say, I'm going to post-access. I'm going to access it first, and then I'm going to update the pointer afterwards. You might not update the pointer at all. So lots of different options, and all of these flags give you these kind of options as how to do things. So lots of different flexible options. The options are indicated by the encodings, right? This is why I give it to you as an encoding, because that tells you what the options are and how to specify them. For each option, we'll look at some examples. And again, there's lots of examples of this stuff in the textbook. So you've got the first ones we're going to look at are the U flag, up, down, the B flag, and the L flag. So the L flag is easy, right? We're storing or we're loading. The B flag is easy. We're accessing a byte or accessing a word. The U flag depends on how you are modifying the pointer based on the offset. You can either add the offset or you can subtract the offset. And the U flag tells you that. U, up, means you're going up in memory from the flag, so you're adding the offset. U0 means you're going down in memory, you're going subtracting the offset, right? The offset is stored as an unsigned number, and so you can't go backwards or forwards from your pointer by changing the sign of the offset. That's what you would do in MIPS, right? In MIPS, the offset is stored as an assigned value, which means you couldn't go above or below that. But in ARM, it's stored as an unsigned value, which means you have to tell it whether you're going above it or below it. So up and down, U flag says you're going above or below. So that's the U flag, the byte flag, and the load store flag. Now we'll look at the immediate offset flag. Okay, there are actually, well, we'll look at the offset. There's 3 options for the offset in ARM. Again, it's similar to the options for the immediate value in data instructions. The 3 options are using a 12-bit unsigned offset, using an unshifted register, or using a register shifted by an immediate amount. Okay? Now these, again, look similar to, but they're not exactly the same as the data instructions, because it would be too easy if they were the same as the data instructions. So first difference is that if you're using an immediate offset, it isn't the aligned immediate offset of data instructions. It's just a 12 actual bits of offset. And what that means, what they're saying in the design is that when you're offsetting from memory, going more than 1,000 bits, going more than 1,000 memory elements is very unusual. And so 12 bits gives you access to 4,000 memory elements, right? 4,000 memory elements, which is 1,000 words in either direction. And that's probably enough. If you have to go farther than 1,000 words in any direction, maybe you should be using a jump instead, right? So mostly the offsets are going to be quite small, but based on this value, based on the 12-bit actual immediate offset, you can go as many as 4,000 memory elements or 1,000 words in either direction, up or down based on the up-down flag. So that's the immediate offset, different from immediate in data operations. Then you can also shift or offset by a register value. Whoa. Where do we go here? There we go. You can offset by a register value. Okay. Or you can offset by a register shifted by an amount. Okay. And that shift looks like a regular encoding for shifts. You specify the shift amount and you specify the immediate amount. Okay. Then the other 2 bits, the P and the W bit, this is where things get a little bit complicated. Because if you're going to update your pointer after you use it, then you can choose to, if you're going to update your pointer when you use it, you can choose to update that pointer before or after. So first thing you have to choose is whether or not you're going to store your pointer, right? Whether you're going to change the value of the pointer when you access it. So if I'm accessing this entry in memory, I might want to then access this entry in memory afterwards, which means I might want to update the value of the pointer after or before I've used it, depending on what order I'm doing things in. Okay? So then W says whether I'm going to change the value of the pointer. P says whether I'm going to change that value before or after I use it. So this is pre or post update with write back. So P0 means I'm going to offset, or I'm going to modify the offset after I do the load or store. P equals 1 means I'm going to modify the offset before I do the load or store. So pre is pre-indexing, whether I'm going to change that offset before or after I do the load or store. And then W says whether I'm going to store that new offset or not. W0 means I don't store the updated offset. W1 means I do store the updated offset. But of course, more complicatedly, is I'm not storing actually the offset, I'm storing the pointer, which is back in that Rn value. So this Rn value might be changed as a result of your load or store, depending on whether or not you're saying update or write back your pointer based on the offset. Okay, so you've got a pointer and you've got an offset. The offset can be specified one of a few ways. The pointer can be modified by the offset in one of a few ways. And then the pointer can be changed as a result of that modification in one of a few ways. Lots of different options, quite complicated, so we will walk through each of these options as we go. This is a piece of note on the sheet. It sits right here. Okay? And these are the different options for how you're going to modify or use that pointer. So the first option is just basic, regular register addressing, right? The address of the data you're interested in is specified by a register, and that's it, register n. Okay? The effective address is just register n. The effective address after you do the instruction is just register n. And the flags for that are 0, 0, 0. So you're not pre-indexing, you're not writing back, and using a register instead of an immediate value. Okay? Now that's a thing to note, by the way, is that the R flag really should be not R or I, right? Because this is whether or not you're using an immediate value as opposed to a register value. Okay? So, and as we'll see here. So now we'll look at an option of changing the pointer before you use it. We call this pre-indexing. The way you specify that in the assembly language makes sense. You put both the register and the offset inside the brackets, which means the effective address is the register combined with the offset, whether that is by an immediate value or by a register shifted by some value, right? R0 means we're using the immediate value. R1 means we're using the register value. So I guess it makes sense. So R1 means we're using the pointer plus some register, right? And we are updating that before we use it, okay? So here's an example. Register, that's our pointer, plus or minus, that's the up-down flag, some other register, and then optionally shifted by some shift amount. And all that's inside those square brackets, which means all of that is the effective address inside those shifted brackets. We'll get to the exclamation mark in a second. Then you can also post-index. This is the other option. And that's when you change the you change the value of the pointer after you use it. So the pointer value is inside the brackets, and then afterwards you put an update. You say, I'm going to change the pointer by some value. Okay? And you can either change the pointer by some immediate value, so the register is 0, or you can change the pointer by some shifted value, some register shifted value, plus or minus some shifted value, register is 1. So those three options first are register by itself, register updated before you use it, that's pre-indexing, register updated after you use it, that's post-indexing. Now we get to write back. This is the part that is really confusing, and it's worth spending a little time to really think about what's going on here. When you update the pointer before you use it, you have the choice to save that new value in the register or not, right? Here you got Rn, that's the base address of whatever you're doing. You might offset that by some number, right? And then you could decide that you're going to be advancing that number bit by bit, and so you want to store that new number so that the next time you do it, you can advance again. Or you might be saying, my base is the top of the array, and I want to go here, and then here, and then here, and then here. I don't want to update that. It depends on what you're doing. So you have the choice, right? You can choose to write back or not. And this is why the W flag, I have this little exclamation mark. In the assembler syntax, you put an exclamation mark there if you want to store that updated pointer back in Rn. So that's why it's optional. Okay, so you can say Rn plus 4, and you can leave the exclamation mark out. Rn is not changed. Or you can say Rn plus 4, and then exclamation mark, and that stores Rn plus 4 in Rn, which means you update and you can work your way down an array that way. Depends on what you're doing. Really clever, really interesting. And you can do that by updating by an immediate value, or you can do that by updating by a register value. Now, where it gets really frustrating, and why this note is in here that you might have seen already, is if you are doing post-indexing, which means you've used the address, Rn, and then you've said, I'm going to change the address by adding some number to it. You're basically saying, I am definitely making a new value for Rn, and so I'm definitely updating Rn. Okay? Now, to me, that would say that the W flag should be 1, because I'm definitely updating Rn. However, cleverness and ingenuity and also trying to compact more things together means that what they've chosen to do is make the encoding 0 for post-indexing in general. Because, and here's the reasoning, I think, is because you're guaranteed to be writing back that value. which means that you don't need to indicate that it's a write back, so you leave it as 0. Should be 0, SBO. And so it leaves an option for some new encoding. If you put W1, then you can do something else, right? That's why I say post-indexing implies write back. If you are updating the pointer after you use it, then you are implying to the machine that you want to store that new value every time. So post-indexing requires write back, implies write back. So the W is redundant. You don't need to set the flag because you know you're writing back, which means you encode it as W0 to leave room for a special case when W is 1. And that just seems overly confusing. Now, the truth of it is most people, most humans, aren't actually doing the encoding, right? Some algorithm, some assembler is doing the encoding, and so it doesn't really matter. But this is, to me, the most complicated part of ARM is these special addressing mode encodings. And so it's worth spending a bunch of time really trying to think about that. And so in the next video, I'm just going to give a bunch of examples to make sure we really have a good example and idea of how to use these and in what circumstances.